When you think about mathematics, what's the first thing that comes to mind? For most people, it's probably something eternal, right?
Shooting absolute, yeah, unchanging.
Exactly, like this flawless crystal structure that's just always been there. But if you actually dig into the history, the human drama behind those perfect equations is, well, it's absolutely chaotic.
It is a profound paradox, and it's really the core tension we found in the source material for today, which is A History of Mathematics, second edition.
Right.
The sources really highlight what makes math unique. Unlike, say, physics or biology, where giants like Galen or even Newton were significantly corrected later.
It was just overthrown, yeah.
Completely. But with math, the results see, and this is a quote, no significant correction, only extension. The theorems just, they stick.
That is the key distinction, isn't it?
Yeah.
The results endure, they compound, but the road to getting them was anything but smooth. It was just full of these intellectual crises and philosophical breakdowns.
Yeah, precisely. And so our mission for this deep dive is to trace that 4,000-year journey. We're going to chart how the three fundamental pillars of math, number, space, and change were repeatedly broken down, found wanting, and then meticulously rebuilt.
All by these brilliant minds who were just striving for more rigor or more applicability.
Exactly.
So if you're relying on GPS or you're engineering a bridge or even just looking at financial data, the incredible precision you use every day is built on the solutions to these ancient fights. We're giving you the shortcut to understanding that messy human story behind it all.
So where do we start?
Okay, let's unpack this right from the very beginning.
The earliest reliable roots we have for mathematics really emerge at the same time in two places, Egypt and Mesopotamia. And right away, scholars find these conflicting theories on how it started.
Was it practical necessity or something else?
Right. Was it, surveying fields that got washed away by the Nile flood every year? Or was it born from, say, priestly leisure and the ritualistic need to align temples and calendars?
And what's so fascinating is that the sources point out you can use the same piece of evidence to argue for both sides.
You can.
The Egyptian geometers, for example, were often called rope stretchers, and they used these knotted ropes to reestablish field boundaries after a flood, a purely practical need. And they used them to lay out the incredibly precise right angles for religious temples.
That dual function is really the birth of applied math. And the Egyptians were very skilled in certain applications. They established a remarkably accurate solar calendar, 365 days, based on deep astronomical observation.
Right, they noticed the Nile flood always came right after the heliacal rising of Sirius.
The brightest star in the sky, so they were clearly good observers.
But then you look at their actual arithmetic, and it has this strange restriction. The source calls it an obsession with unit fractions.
They absolutely did. They were constantly using 1/2 and 1/3, but they seemed to work really hard to avoid more complicated fractions.
Why was that?
Well, they lacked a really flexible notation system, so they developed these rigorous systematic methods to break fractions down. The famous Rhine Papyrus, for instance.
Oh, yeah, I've heard of that.
It includes this extensive 2/n table. So if they needed to express, say, 2/39, they wouldn't write it that way. They'd decompose it into a sum, like 1/26 plus 1/78.
Seems so cumbersome to us.
It does, but it maintained a certain purity in their system.
Okay, so you contrast that with their contemporaries in Mesopotamia, the Babylonians.
Right.
Who were, they were mathematically far more advanced. And the reason for that just boils down to one monumental invention about 4,000 years ago.
Positional numeration.
Written in cuneiform, yeah.
And that idea, where the value of a digit depends on its placement, that allowed them to represent vast integers, huge numbers, and tiny fractions without endless repetition of symbols.
And this flexibility just gave them incredible algebraic power.
It did, even without our formal concept of proof. They were solving problems that we would immediately recognize as quadratic equations. They routinely tackled this normal form problem. Find two numbers when you're given their product and either their sum or their difference.
Which is pretty advanced stuff.
And their method was astonishingly sophisticated. They could take a complex quadratic, something like x squared plus bx equals c, and through a clever substitution, reduce it to a much simpler solvable form, like y squared plus y equals ac.
Wow. So they were already thinking abstractly about the relationships between quantities.
Exactly, even if their goal was still just to calculate a specific numerical answer for a specific problem.
So this all raises a fundamental question for our story. We have the Babylonians with sophisticated calculation, but no general proof. Why did math shift from these, highly effective techniques to abstract thought and philosophical rigor?
That shift happens decisively in the Greek world. That's where the focus moves sharply from the Babylonian practice of logistic or practical calculation to the Greek idea of arithmetic, which was abstract thought about the very nature of number.
And you have figures like Thales and Pythagoras who just fundamentally changed the game. The source compares them to Homer and Hesiod in literature. They basically created the intellectual tradition.
And this transition, it immediately leads to the first great intellectual crisis in mathematics.
The Pythagorean crisis.
Exactly. The Pythagoreans were guided by this deep philosophical faith that all is number. They believed everything in the universe could be represented by a ratio of two whole numbers.
So what broke that faith?
A simple geometric discovery, the diagonal of a unit square. They discovered what we call incommensurable magnitudes.
Meaning you can't compare them?
You can't. When you compare the length of the diagonal to the length of the side, you realize there's no common unit, no smallest fraction that can measure both of them evenly.
That diagonal is the square root of 2. And if you're a Pythagorean, believing everything has to be a nice, neat ratio of whole numbers.
The existence of a number that defies ratio is a catastrophe.
A total catastrophe.
Absolutely. Their foundational belief was demolished. Theodorus of Cyrene is the one credited with first showing the irrationality of the square root of 2, and this realization meant that number theory, arithmetic, was, by itself, just inadequate to describe even the simplest properties of geometric space.
Yeah, and that crisis, that divorce between number and space, is what sets the stage for Euclid's Element.
It's hard to overstate the importance of that work.
It's just unique in history. It wasn't really a work of original discovery, was it? It was more of a textbook.
Exactly, a synthesis. It was noted purely for its incredible organizational structure and its expository skill, just taking all this disparate knowledge and building it up logically from a set of axioms.
And it was an instant success. It superseded at least 3 earlier elements that we know of, and its longevity is just, it's mind-boggling.
An estimated 1,000 editions. It's second only to the Bible in publishing history.
So when you open the Elements, you realize the Greeks, because they couldn't trust these irrational numbers, they started using geometry as algebra.
That's a perfect way to put it. They mapped complex algebraic relationships onto visual forms.
Can you give us an example of that?
Sure. Proposition 1 of Book 2, for instance. When we read it today, we realize it's a geometric statement of the distributive law. The idea that a times b plus c equals ab plus ac. But they proved it by showing how the areas of rectangles related to one another.
But it also preserved practical wisdom.
It did. Book 7 opens with Euclid's algorithm, a highly efficient method for finding the greatest common divisor of two numbers that we still use in computation today.
Okay, so fast forward a century, and you find the pinnacle of applied Greek genius in Archimedes of Syracuse.
Rightly described as the leading mathematician of all antiquity.
And Archimedes seamlessly connected that abstract rigor of Greek geometry to the physical world.
Absolutely. Take his work on the equilibrium of planes. He used geometric proof to establish the law of the lever, showing that balance depends on weight times distance.
And his most famous discovery, of course, the hydrostatic principle.
Detailed in around. On floating bodies. That principle, that a solid in a fluid loses weight equal to the weight of the displaced fluid, is fundamental for naval architecture, for physics. And he derived it through geometrical reasoning, not just trial and error.
So we have this incredible, sophisticated Greek system. But how did it survive the decline of the classical world? How did we not lose all of this?
This is where the story shifts geographically. We move into the Arabic hegemony. And their intellectual achievement was a miracle, not just of original discovery, but of rapid absorption. They were the absolutely crucial vehicle for preserving and transmitting knowledge.
And they weren't just preserving Greek classics like Euclid and Ptolemy.
No, they were also importing revolutionary ideas from the East, from India specifically.
They acted as this conduit.
A perfect conduit. They translated the Greek knowledge, safeguarding it, and at the same time brought the Hindu-Arabic system with its 9 digits into Europe.
We really have to pause and acknowledge the impact of those Indian contributions. The sign function in trigonometry came from India.
It did, and crucially, the earliest undisputed occurrence of a zero symbol is found in India, in an inscription from 876.
And the concept of zero, not just as a placeholder like the Babylonians used, but as a number in its own right, that was a fundamental conceptual leap.
It made modern positional mathematics possible. Without it, the Renaissance explosion of algebra simply doesn't happen.
And that explosion starts with a bang in Renaissance Europe, driven by these intense personal rivalries and public challenges.
The cubic equation became the Everest of 16th century math. The famous story of Cardan solving the cubic equation x cubed plus px equals q is central to this.
Which he phrased rhetorically, didn't he? Something like, the cube and 6 times the side be equal to 20?
Exactly.
So why was solving the cubic such a huge breakthrough?
Because the algebraic solution required using negative numbers, which were still controversial, and even more startlingly, it required using the square roots of negative numbers.
What we now call imaginary numbers.
Right. And Cardan, even though he found the solution, was deeply distrustful of them. He reluctantly called them numeri ficti, fictitious numbers. The algebra literally forced the concept into existence.
And this expansion of what a number could be created this urgent need for better symbols, for standardization.
For sure. Robert Ricord addressed this when he introduced the equal sign in 1557. He argued for it because, as he put it, no two things can be more equal.
I love that. It shows that human desire for clarity emerging right alongside the complexity.
But even with new symbols, the concepts were slow to evolve. Vieta, for example, he pioneered using letters for parameters and unknowns, which was a huge step toward generalization. But he still only allowed positive roots for his equations.
He had these philosophical limits.
He did. It was really with Albert Gerard in 1629 that the definitive conceptual leap happened. He was the first to clearly state the general relations between roots and coefficients for equations, and, critically, he explicitly permitted negative and imaginary roots.
Which anticipates the whole idea of the number line and the complex plane.
Exactly. And meanwhile, on the practical front, Simon Stevin, back in 1585, made this incredibly important plea for everyone to adopt decimal fraction.
To get rid of the old system.
To get rid of the sexagesimal and unit fractions that were still common. He helped smooth out the arithmetic, really paving the way for the next and arguably most explosive revolution, the study of change.
The 17th century. The arrival of infinitesimal analysis, calculus.
And it was driven by the urgent needs of physics and astronomy. Early pioneers like Kepler and Galileo were using Archimedean methods, but they deliberately bypassed the incredibly laborious logical niceties of the method of exhaustion.
They just needed speed.
They needed speed, even if it meant sacrificing some rigor for the time being.
And this freedom from the old rigor is what led to the independent discovery of calculus by Newton and Leibniz.
Both established the core principles, but it was Leibniz who really provided the intellectual architecture that won out in the end. He coined the term transcendental function, and he developed the superior notation.
The familiar didax.
The didax for differentiation, and that elongated s, the integral sign. That notation made the relationship between the two operations crystal clear.
Which is the fundamental theorem of calculus.
Exactly. The idea that differentiation and integration are inverse processes. It's the grand connection that showed that, speed and distance or area and rate of change are just two sides of the same mathematical coin.
But the very speed and lack of rigor in that first discovery, using concepts like infinitesimals, these quantities smaller than any number but not zero, that meant the next 2 centuries had to be dedicated to cleaning up the mess.
The quest for rigor was paramount. Philosophically, infinitesimals felt shaky. It was like a return to Zeno's paradoxes from ancient Greece.
So how did they fix it?
Well, Lagrange, late in the 18th century, he attempted to eliminate them entirely. He wanted to define analysis based purely on derived functions, f prime of x, f double prime of x, and so on, based on Taylor series.
But his system, which was meant to be purely arithmetic and not rely on limits, it ultimately failed, didn't it?
It did. The sources make it clear that his method required him to assume that every function could be expanded in a series, which is a property that later needed the very concept of limits to prove it. He tried to build the house without the foundation.
So the 19th century becomes the era of the foundation builders. And Cauchy was absolutely key here.
Cauchy provided the necessary rigor by defining the definite integral not as an antiderivative, but as the limit of a sum, what we often write as S sub n. This put the whole concept on a clear, verifiable footing and paved the way for modern integration theory.
And at the same time, the concept of space itself was breaking, just like number had with the Pythagoreans. For millennia, Euclidean geometry was it. It was considered absolute truth.
And that certainty was shattered by Lobachevsky, who's rightly called the Copernicus of geometry. He showed that if you negate Euclid's parallel postulate,
The idea that only one parallel line can go through a point.
right, if you negate that, you don't get mathematical chaos. You get a perfectly self-consistent, non-Euclidean system.
Which was revolutionary. It showed geometry wasn't a description of reality, but just one system among many.
And we should note, Gauss had the idea decades earlier, but kept it unpublished. He was afraid of the public outcry.
So these parallel crises, shaky foundations in calculus, non-absoluteness of space, led to a need to definitively ground the number system itself.
And that's where Dedekind steps in 1872. He brought back the irrational numbers, but on a solid arithmetic footing, completely detached from the shaky intuition of geometry.
How did you do that?
He defined irrational numbers using what he called cuts. A cut basically divides all rational numbers into two sets. This allowed him to define numbers like the square root of 2 precisely, based purely on sequences of rational numbers.
And this definitive grounding of numbers culminates with David Hilbert, who ushers in the modern era of pure mathematical abstraction.
Yes, where the focus moves from what the math describes to the internal logical consistency of the axioms themselves.
Which he captured in that famous statement about geometry.
One must at all times be able to replace points, lines, planes by tables, chairs, beer mugs. The objects don't matter, only the relationships between them.
It's an incredible intellectual journey. We started this deep dive with, practical ropes in the mud of the Nile, driven by simple necessity, and we've ended with pure abstract mathematics where points could literally be beer mugs.
And what the history overwhelmingly shows is that paradox we started with. Mathematical progress is cumulative. Once a result is established, it endures. That's the no significant correction principle.
Right.
But that steady growth is continually fueled by these intellectual catastrophes, the discovery of the irrational, the breakdown of Euclidean certainty, the crisis of the infinitesimal, and by these unexpected fusions of ideas.
So what does this whole story imply for us? We've seen that the quest for absolute rigor defined the 19th century. And at the very beginning of the 20th, David Hilbert challenged mathematicians to accomplish the ultimate goal: prove the internal consistency of arithmetic.
To show, once and for all, that our core number system would never lead to a contradiction.
Exactly. And you may be surprised to learn that later work, specifically Gödel's incompleteness theorems, showed that within the system of arithmetic, there are certain clear-cut statements that can be neither proved nor disproved. What does that startling result imply about the ultimate limits of absolute certainty, not just in mathematics, but in all of human knowledge? That's a deep dive for another day.